Okay, so today's video is going to be on simple harmonic motion. So to start this off, I'd like to take a look at this simulation. If I hit play during this simulation, we see that there's two springs on either side, spring 1 and spring 2, and we have a block that is oscillating back and forth. And this block oscillating back and forth is repetitive, so it's harmonic, and we call this simple harmonic motion. Now, a couple things to point out here. If I check the velocity and the acceleration boxes, what you will notice is that the velocity, the purple line right here, is going the fastest when it's in the center. Its acceleration vector always matches the direction of the spring. Okay, so these two are always pointing in the same direction, and they are proportional to each other because F equals ma. And we also notice that the acceleration and the force is largest when it's at the extremes, okay, on either side. So let's take a look at this on our notes. All vibrations or oscillations are ultimately due to some type of restoring force. And that force is trying to bring the mass back to its original position. Okay. This effect, if the force follows Hooke's law, what we say is that that spring is a Hookean spring. Okay, and essentially that it follows Hooke's law. So Hooke's law is the force on a spring is equal to the negative of the kx. And the negative sign, all that means that it is a restoring force. And the force is proportional to the displacement. So if we take a look at graphs, we want to plot acceleration and velocity as a function of time or displacement. So let's do it first versus displacement. So we want to describe how the velocity, and I'll do velocity in this blue. So we essentially are oscillating back between a positive amplitude, I'll call that A, and a negative amplitude, the two extremes that you saw in the case. And we know that the velocity is 0 at the extremes because it actually was turning around. And right in the middle, okay, a position of 0, the velocity was a maximum. And let's say the velocity is positive. Now, to connect these 3 points, we have to do a little bit of reasoning. We know that the elastic potential energy at the edge is equal to the kinetic energy in the middle. Okay, and this is 1/2 kx squared. This is 1/2 mv squared. The halves cancel out. All I'm going to do is square root both sides, and what we end up getting is that x is directly proportional to v. And the reason this is important is because now it tells me that I connect my points with a line. So let's do the acceleration now in red. Now the acceleration, if you notice, was at a maximum at the extremes. So at negative a, let's say it was a positive acceleration. And then at positive a, let's say it was a negative acceleration. And so in order to connect those two, we know that a is equal to F over m, second law of motion, and that the force here is Hooke's law, the kx over m. And the reason this is important, now we can see that x is directly proportional also to x, as a is directly proportional to x. So, and then we also know that in the middle, the acceleration 0, it's changing its acceleration. The force is essentially going from one spring to the other. So we end up getting is a linear graph here as well. Okay, now versus time. So let's say we're plotting it versus time. So we have velocity. Let's let's keep this consistent. Let's do velocity in the blue here. So the blue line will represent the velocity, and a red line will represent the acceleration. So what's going on? Well, we said that, let's say the t is our cycle, so it's one full cycle, so it's a round trip. So let's say that the velocity starts off in the middle. We start off in the middle, where the velocity is at an extreme. Okay, so velocity, so we're saying that our original position is 0, so right in the center of our oscillation. So it's at a maximum there. Then a quarter of the period, in other words, when this would be when the position is on the far end. Okay, let's take a look at that simulation again. So a quarter of the period is when it goes, so if we start now, a quarter, half, 3/4, and we have a full period. We have a full oscillation. So with that in mind, the velocity goes from its maximum value. A quarter of the time later, it's going to be at 0. Another quarter of the period later, it's going to be at the same value, just negative. And then you end up getting a nice sinusoidal graph. Okay, and this one, what graph this looks like, right, is our cosine graph. So now, in order to get the acceleration, we're going to use a trick. We know that the acceleration is the slope of the v versus t graph. And with that in mind, what I'm going to do is I'm going to sketch in some tangent lines. I'm going to sketch in some tangents at my 5 values. So when the velocity is at a maximum, the acceleration is at 0, which we kind of see that here as well. And we start off going in a negative slope, so sometime later. And I don't know how these two values compare to each other. The amplitude here, I don't know how these two compare, but I'm going to assume it's less. But it could be just as much as it could be more. Here we have 0, okay, and here we have 0. And in between we have a positive number. And so what we see here is that this one looks like not just a sine graph, but actually a negative sine graph, since it goes into the negative region first. Okay, so let's derive an expression for velocity as a function of position. Okay, with keeping the graphs in mind. So we're going to do two cases. Case 1, we want to figure out when the speed is a max. So we know that if we have this block oscillating back between positive A and negative A, that when the position is 0 in the middle, it's going to be at its maximum speed. So what I'm going to say is that the potential energy when it's at one of the extremes, and it doesn't matter which one it is, the elastic potential energy is going to be equal to the kinetic energy in the middle. So I have 1/2 kx squared equaling 1/2 mv squared. And we see the halves cancel out. Okay, now the position that is a maximum, I'm going to call this actually just positive A. So I'm going to replace x with a squared, and that's equal to mv squared. And this is my maximum value. So my v max, if I solve for v, is k over m times a squared, and it's the square root of all that. And so what I'm going to do is I'm actually going to pull out this a squared. It's under the square root, so I just get a times radical k over m. And that's going to be my maximum speed. So let's write that, v max. And that's important, so we're going to put a box around it. All right, so case 2 is if I want to describe the speed at anywhere in between. So if I want to be able to describe the speed anywhere in between. Well, anywhere in between, it's not going to have all of its energy is not going to be just kinetic, but some of it is also going to be elastic potential, because the spring is still on stretching between negative A and 0. So I'm going to have, at the extreme, I'm going to have 1/2 ka squared, just like before. This is not changing, that all of the energy is elastic potential at our a's. But everywhere else, it's going to have some velocity, so it's going to have some kinetic energy, plus some elastic potential at the other position x. So x is basically anywhere in between zeros and a's. And so I could see the halves cancel out just like before. We're going to do some algebra to solve for v here. So I'm going to subtract kx squared, and I'm going to pull out a k. So I get a squared minus x squared equaling, parentheses, equals mv squared. And then if I solve for v, I get k over m times x squared minus a squared minus x squared, and then square root that whole thing. Now I'm going to do some little trick here. I'm going to pull out an a squared to each term. Okay, and you could say, well, how can I pull out an a squared here? There is no a squared. But what I'm going to do is actually I'm going to multiply both the top and bottom by a squared. So really I'm going to write an a squared here over a squared. And I could do that because this really is just 1, so it's just going to make it look a little bit different. And by doing so, what I end up getting is the square root of k over m times a squared times 1, because when I pull out a squared, that's just left over 1, minus, I pull out an a squared here, I get x squared over a squared. And so I could do the same thing with the a squared, and I'm going to actually write this like this, and you'll see why I'm doing that. So I'm going to pull out the a, and so I have the square root of k over m, and then I also have the square root of 1 minus x squared over a squared. Okay, now the reason I wrote it like this is because if we look what this is up here, this is actually stands for the maximum speed. So we have maximum speed times 1 minus x squared over a squared. Okay, this right here shows what we have, what we call a simple harmonic oscillator. So this is what we refer to as a simple harmonic oscillator, if it follows this format. Okay, so if any other type of situation follows this format, we can say it's a simple harmonic oscillator. Okay, so this is a big deal. So this is the velocity at any other point. And I'm going to exclude that SHO. Okay, so try out this example, but I will tell you what I shared, what I got. You have to first find K, so I got 357. Okay, and that's newtons per meter. And then if you go through and solve for the speed, which is what it's asked, I got 1.34 meters per second. Okay, so let's take a look at these three graphs. If I want to graph the elastic potential energy versus position, we know that elastic potential energy, the 1/2 kx squared, so elastic potential energy is proportional to x squared, meaning that we're going to get a parabola. And we know that when it's in the center, so when x is equal to 0, that it is got 0 elastic potential energy, and when it's at the extremes, a and minus a, that the elastic potential energy is at a maximum. So I'm going to put whatever that number is up here. And I'm going to connect these with a nice quadratic, okay, or quadratic-like, okay. And then I'm going to jump right over to here. So basically we know that when the elastic potential energy is at a minimum, we know the kinetic energy is at a maximum, and vice versa, that when the elastic potential at a and minus a, that when the elastic potential energy is at a maximum, the kinetic energy is at a minimum. So I get basically a upside down parabola, also known as a sad parabola. You got a happy parabola, sad parabola. So let's kind of plot that of PES versus kinetic. So when PES is at a maximum, KE is at a minimum, PES is at a maximum, and vice versa. And we get a nice linear relationship. So that's all for now.